I know it's been a long and arduous day, but thank you for making it to our last talk. Up next, we've got Srinivasan talking about quantum learning theory.
Yeah, thanks. Thanks for the intro, and thanks for inviting me. I would like to thank the organizers. I don't see Andrew and Ziaudi, but I thank them when they see it. So I'm right now at MIT. I just started a postdoc there, but most of the work that I'm going to be talking about is work that I did with Ronald DeWolf when I was a PhD student at CWI. And my work will be a lot more on, I mean, if you look at classical machine learning, there are two kinds of, there's something called computational learning theory, where there are things that you can prove formally, you can prove in formal separation, and then you have this other side where you have graphs and, yeah, this method works, but we don't have a formal proof and so on. And I think my talk will lean more on the formal first side, where I'll see what I can prove and what I can't prove. Okay, before I get more formal, let me just start with the standard stuff. What is classical machine learning? I mean, the grand goal in classical machine learning is to enable AI systems to improve themselves. This is vague and this is sort of ambitious. Something that we settle for is, can we learn something from given data? Can we make predictions? Can we find patterns in them? And so on and so forth. And indeed, I mean, recently we have achieved a lot of success in this field, and one of the primary reasons is because of deep learning. Deep learning is extremely good at image recognition, natural language processing, even the games of Go, chess, and so on. And there are a few reasons why recently we have been obtaining so much success in the field, and one of the reasons is there's a lot of available data. So I mean, there is so much data that there's a lot of training data, and we can train our systems to do much better on future test data. There's increasing computational power, and in the algorithms community, we are coming out with much better algorithms that are actually useful in practice. But what do I care about it? What can quantum do for machine learning, or what can quantum computing have anything to do for machine learning? And informally speaking, I mean, there are two things that I can be talking about here. One is either there's just a quantum computer that is fed classical data. So I mean, you can just quantumly improve a classical algorithm, or you could assume that you have quantum data fed to a quantum computer, and can we get any speedups? And indeed, if you look at this paradigm, I mean, there have been some results in this direction. If you look at clustering, then there is principal component analysis, and there's perceptron learning, and there's recommendation systems. All those recommendation systems was recently dequantized, but I still think there is some polynomial speedups, which essentially most of the other problems also kind of give you quantumly. But again, as I started my talk with, I'm kind of interested not in specific problems, but is there a framework which classical computational learning theory people care about? And is there a quantum analog of this classical framework? And can we improve something there? Okay, and so I have to define this framework that I'm talking about. And there are some basic definitions, basic terms that I'll be using very often in this talk. So it's better that we all just get used to this terminology. The first is a concept class. So this is just a collection of Boolean functions, and Boolean functions on n bits. And I'm restricting to Boolean functions for simplicity. I could have also taken real valued functions, which are represented succinctly maybe. And a target concept is just one concept from this concept class. So script C was my concept class. Little c was just a function from the concept class. A distribution D is just a distribution on all possible n-bit strings. And a labeled example is a pair x, c of x, where x is drawn from the distribution D. So you have a concept class that is just a collection of Boolean functions, target concept that is one function from the concept class, and then a labeled example is x, c of x, where x is drawn from this distribution D. Before I formally define this framework and so on, let me just tell you what a learning algorithm even looks like in this framework. So he's my learner. The reason I chose a Pac-Man will become evident in a few slides. So this Pac learner knows my concept class. So this is the concept class that is known. But he doesn't know this. And his goal is to learn this. That's what his goal is. And the way he's given information to learn is someone just samples an x according to this distribution D and gives him x, c of x. And he says, sure, that's nice, but I want more information to learn this target concept. Someone samples another x according to the distribution D and gives him another x, c of x. And he says, okay, great. And this process keeps repeating on. And at some point, he says, okay, I think I'm good enough right now. And he says, we are kind of liberal in the sense like we don't want him to exactly reproduce C. Just output a function that is close to C. That's all his goal is. He processes this much information, and at the end, he just needs to output a function that is close to the function that he's trying to learn. Okay, now that this is how a classical learning algorithm will look like, before I give you a formal definition of what a close means and so on, let me tell you what a quantum learning algorithm looks like. First things first, Pac-Man becomes quantum. So this is apparently the new quantum Pac-Man. And that's that. So essentially, this is just a quantum computer. That's it. And I'm going to be assuming data is quantum. And I'm going to be assuming a data model that was introduced by Schutte and Jackson back in '95. So they just assume that you have a coherent superposition of x comma c of x's, where the amplitudes are given by the square root of the distribution d. I mean, in the end, we can talk about why is this a good learning model, why is this good data, and so on. But for now, let's just assume I'm working with this data model. And first things first, why is this a natural generalization of the classical learning model? Let's just say, I mean, a quantum learner could just choose to measure this all the time. And when he measures this, he's going to get an x comma c of x with probability d of x. But that was precisely how a classical learner was defined. He kept getting information x comma c of x when someone sampled x according to the distribution d. So this is my quantum learning model, quantum learner, quantum data. And what's the motivating question for my talk is the following. So let's fix a concept class script C that is just a collection of Boolean functions and a distribution D that is a distribution on n-bit strings. This is a classical learning algorithm, classical learner, classical information, quantum learner, quantum information. What are the concept classes and what are the distributions where fewer number of quantum examples suffice for a quantum learner? This is really what I care about. Can I formally show there exists a concept class and a distribution for which actually a quantum computer or quantum learner can process fewer quantum examples and actually do well? Now that I've been vague and kind of given you the intuition of what my learning model is, I'm going to get slightly technical now. So let me formally define my model of learning, and it's called the probably approximately correct model of learning, and it's called the PAC learning. So that's why the Pac-Man. And this was a model that was introduced by Leslie Valiant in 1984. And I mean, if you look at computational learning theory, almost most of the well-known results are kind of phrased in the PAC model of learning. I mean, if you give a concept class to a classical computational learning theorist, the first thing that he might ask you is it learnable in the PAC setting? So this is really something that they care about. So a concept class is just a collection of Boolean functions, and D is just a distribution on n-bit strings. And I'll define what I mean by close a couple of slides back. So a learner for a concept class should output, so he's trying to learn this little c. That is a target concept. He should output a hypothesis H that is close to C with respect to a distribution. So what I mean by that is he should output a hypothesis H that is close to C on the Boolean cube, where this closeness is measured according to a distribution. I mean, if you find this distribution slightly annoying, you can just think of C just being a truth table, H, he should output another truth table, and on most points, these truth tables should be close. And again, in this, there are two models that I care about in this talk. And the first talk is a distribution-dependent learning. That is, you fix a distribution D, and you want that for every concept, so little c is unknown to him, for every concept with high probability, he should output a H that is approximately correct. So probably, he should approximately correctly find the concept that he's trying to learn. So that's the distribution-dependent learning. So the reason it's distribution-dependent is because he knows D. He knows what is the distribution under which he's being tested, and he's learning, and the one he's going to be tested later on. And the second model, which was the original model that Leslie Valiant introduced in 1984, is the distribution-independent learning, where you remove this condition, fix D. So he doesn't know anything about the distribution. D is unknown, script C is known, he just doesn't know what he's trying to learn. So we say an algorithm learns the concept class according to in the PAC setting, if for every distribution and for every target concept with high probability, he can output a hypothesis that is close to the target concept. Again, the only difference is here I fix a distribution and he has to learn according to the distribution. Here I say for every unknown distribution, he should do well. So this is really people are colloquial when they say packed learning, but when they talk about distribution dependent, but I'll be more specific throughout this talk, I'll say distribution dependent or distribution independent, just to remove any ambiguity. So what is the complexity measure that I care about? I mean, I've kind of already alluded one complexity measure, that is a sample complexity, the number of examples that the learner sees. Okay, so that is just the sample complexity. So a quantum learner, the sample complexity will be the number of quantum examples. For a classical learner, that is just the number of x comma c of x's that he sees. Then there is time complexity. That is the amount of time that he takes to learn at concept class. So it could be that the sample complexity is small, so he just takes a small number of examples, but he needs to do a lot of post-processing, in which case the time complexity could be big. And let me get to the results that I'll be talking about here. I'll be talking about a few results, and the first part will be about the strengths of quantum examples. When do quantum examples provide an advantage? And the first thing I'll be talking about is a concept class of Fourier sparse Boolean functions, and I'll be fixing a distribution, the uniform distribution D. I'll get to these definitions in a couple of slides. The next will be talking about a concept class of DNFs. I mean, in the previous talk, we saw satisfiability is a CNF, but but I'll be talking of DNFs. I'll define this more clearly in a bit. And then I'll be talking about the coupon collector problem. This is a very cute problem that people in theoretical computer science are introduced to very early on, like in undergrad course, and I'll be telling you why quantum examples actually help there. And finally, I'll be talking about the weaknesses of quantum examples. I'll give you, if you look at the packed model of learning, I will show that quantum examples are actually useless. I mean, well, in the sample complexity sense. And I mean, the way I structured this talk is, both these results use a powerful tool called Fourier sampling, and both these results use another tool called the pretty good measurement. So if supposing you, at the end of this talk, you realize that, okay, these things are too artificial and contrived, but I still want to contribute to the field, you just need to know these two tools, and you can already start working in the subject. So let's first talk about Fourier sampling.
May I have a question? So in packed learning, you have arbitrary distribution.
Yes.
But now in the quantum setting, you extend it to quantum distributions, or you still remain in the realm of classical distributions? And if so, then how do you draw the quantum samples from the classical distribution, or how should I think about the distribution?
The distribution stays the same. The question was, is there something called a quantum distribution that I'm working on in the quantum pack setting? And no, it's a standard classical distribution. It is just that it's unknown to the quantum learner. So he has a quantum state where the amplitudes are given by a distribution which is unknown to him. That's about it. There is no quantum distribution that's coming into the picture here. You can stop me again and ask me if it still doesn't answer your question. Sure.
So mathematically, in packed learning, you would say that for every classical distribution, your learner can, the formulas in the quantum learning mathematically starts exactly the same way.
Yes, it does.
For every classical distribution, there is this quantum learner. However, that quantum learner somehow gets like superposition of, but like if there is a classical distribution, like how can he get a superposition? Like what does it mean? So the classical learner gets one classical example according to that particular distribution.
Yes.
So what does it mean that you get a superposition according to a classical distribution? What does that mean?
It just means that you have a coherent x comma c of x where the amplitudes are given by this unknown distribution D. That's about it. I'm just saying that the unknown classical distribution is encoded in the amplitude of the quantum state.
Okay.
So for every unknown classical distribution, you're given a quantum state whose amplitude is given by the square root of the unknown distribution.
Okay.
That's about it.
This sample complexity just the number of copies of this identical state that you're going to provide?
Yes, every time a quantum learner is going to get the same identical state,
Okay.
quantum state. Yes, absolutely right. Yeah, I mean, you should just stop me whenever you have questions. Right, so first thing I'll be talking about Fourier sampling. And this is really a powerful tool when you're working under the uniform distribution. So what's the idea? Let's see just be a Boolean function. So it maps n-bit strings to plus or minus 1. Then the Fourier coefficients of this Boolean function are given by this complicated looking expression, but this is just the inner product between C and the parity function on S. Okay, maybe you don't need to understand this completely, but what Parseval's identity states is the following. So if we look at the sum of the squared Fourier coefficients, this is equal to the expected value of C of x squared. But recall that C of x was plus or minus 1, so C of x squared is just 1. So this expectation is just 1. So what does this mean? This means that C hat of S squared actually forms a probability distribution. Okay, so that's nice, first thing. And what's even more interesting is we can actually sample from this distribution. And the way we do that is the following. So let's just say this was my quantum example. Earlier I had square root of d of x here, but since d was uniform, it's now 1 over square root 2 to the n. And if you apply a Hadamard and measure it, you can actually produce the state, a superposition over all s's, where the amplitudes are given by c hat of s. And if you just choose to measure this, you obtain an s with probability c hat of s squared. So using just a constant number of uniform examples, you can actually sample from the Fourier distribution. And classically, if you look at it, if you want to sample from this distribution, so what I mean by classically, you're not given a quantum example, but you're just given x comma c of x. This is not, you need a lot more copies classically. In fact, maybe even omega n number of copies to sample from this distribution. Okay, let's just look at a couple of quick applications on how this is useful actually. Now, the first thing that people do is looking at linear functions. So this is just a concept class where every Boolean function is just indexed by an n-bit string s, and cs of x is just the inner product between s and x. And classically, if you want to solve this, you need omega of n classical examples. You just get many x comma c of x's, and you just solve a linear system of equations to get s. But quantumly, Bernstein and Vazirani in 93 showed that just one quantum example suffices to learn C1. So this is like a provably big speed up. And then there's another thing which was slightly more recent, it was back in 2009 and was by Atici and Servadio. So they looked at the concept class of L juntas. So what's a junta? So a Boolean function, I've been defining it for so long as a function that depends on n bits. But let's just say it doesn't depend on all n bits. It just depends on a small subset of L bits. So if a function just depends on a small subset of its input bits, we call it a junta. And let's just say we look at the concept class of all Boolean functions that are just L juntas. And classically, it's a notoriously hard open problem to learn this concept class just for log n juntas. I mean, people would die to solve this problem. It's that important for classical learning theory people. But quantumly, Atici and Servadio showed you can actually solve it in polynomial time. So if you put L equal to log n, using polynomial number of quantum examples and in time polynomial in n, you can actually learn this concept class, which we are struggling to even understand classically. Okay, and the first result that I would talk about is the class of functions that are called K Fourier sparse. So these are functions for which the number of non-zero Fourier coefficients is at most k. Okay, let's see, why do C1 and C2 fall under something like this? So if you look at C1, the number of Fourier coefficients is just 1. So it's 1 Fourier sparse. And if you look at C2, all the Boolean functions are 2 to the L Fourier sparse. So let's just say I define this concept class. That is a class of functions that are K Fourier sparse. Then clearly C1 contains this concept class, and C2 is also contained in this concept class for L equal to log K. And the question that I want to answer is, can we learn this concept class in more generality? Yes?
Between the classical and the quantum computation for the junta problem, only the computation complexity is different, or the sample complexity is also? I think only the computation
Yes.
Only computation, right?
That's because classically it's the same. You can solve a linear system of equations. You get. Yes, you're absolutely right. Yeah, I think n cube number of samples suffice, but in time it's quasi-polynomial in n or something. N to the omega. Yes, you're absolutely right. Right, and some of you might be wondering, yeah, this is just too artificial. Why do I care about this? I mean, if you look at, there's an entire field in classical big data or whatever you call it on sparse recovery where people look at real valued functions that are sparse in the frequency domain. So let's just say you have a function. It has 2 to the n coordinates. You apply the Fourier transform, and it's just very sparse in the Fourier domain. Then can we learn this concept class in a slightly different model of learning? And it so happens that you can actually learn it, and this is extremely important in questions like image recognition and so on and so forth. Although the model here we're looking at is Boolean functions, and the learning model the learning model is slightly different, but I would like to motivate all this by saying people actually do care about it. We're looking at a restricted setting and asking what can we formally show about this. That's more important for me. So again, this is the concept class that I want to learn. And I'm given the uniform distribution, and I want to exactly learn C. And a couple of years back, Regev and Habib actually looked at this problem, and they showed that n times k, number of classical examples, x comma c of x, are necessary and even sufficient to learn the concept class. So remember, k was a number of non-zero Fourier coefficients in C, and C was a Boolean function on n bits. And what we show is actually, if you have these coherent quantum examples, just k to the 1.5 quantum examples suffice. So it's completely independent of the truth table size of C. You could have an extremely long truth table for C, but as long as you promise me it is just sparse in the Fourier domain, a few number of quantum examples already suffice. So this is a pretty big speed up over the classical algorithm. And we also give a lower bound of omega of k. So we know the right answer sits somewhere here. And let me quickly sketch what goes on in here. And I'll just give you a quick sketch of this upper bound. Fourier sampling, of course. So let's just say you have these uniform examples. What I stated earlier was if you have these examples, then you can also sample from the Fourier distribution of C. And that's what we're going to do. So our algorithm is the following. You just keep sampling from this distribution. You keep seeing S1 drawn from this distribution, S2 drawn from this distribution, and you keep collecting them in a set script B. And at some point, you're going to collect the entire Fourier span of C. And I mean, you keep collecting these samples, and at some point you have collected V. And the question is, how long does it take you to collect V? We show that if the Fourier dimension of C was R, then R times K quantum examples suffice to learn B. And then using an F2 invertible map and using the classical result, we show that R times K classical. So in this step, we have just learned the Fourier span, but at this step, we learned C completely. Okay, and finally, there was a result that shows that if you have a K Fourier sparse Boolean function, then R is at most square root K. So we get R at most square root K, and this product becomes K to the 1.5. I mean, if some of you are feeling this is just too technical and what's going on, I don't even care. What I want to really emphasize is the following. The second to the last part, you could have just given it to a classical machine learning person and asked it to solve it. All the crux that we're using is the fact that we can sample from the Fourier distribution. Really, that's the only quantum thing we are doing. The rest of it was all, well, I mean, there is some extra work to be done to get second and third, but all this was already done classically. Fourier sampling is really the only quantum thing that we are doing here. So you can think of it as just a toolbox to hit classical learning theory, quantum learning theory. All right, let me go to the next problem that I care about is the disjunctive normal forms. So I mean, sorry.
Just a question about the previous one, pretty long.
Yeah.
So I guess the Simon's problem sort of fall into this picture. Can you think about it?
Well, I mean, the domain is not the entire Boolean cube, firstly.
Right, but I mean, I could think about the class of Simon's functions and the distribution, like uniform distribution, and trying to learn, the K.
Well, so actually, things don't work out very well if you don't have the entire uniform distribution here. Let's just say you have the uniform distribution on a subset, which is what you might have for Simon's problem. Then it's not clear that you can sample from the Fourier spectrum there.
Well, but I mean, I guess in Simon, I want to query with the uniform superposition, right? When I'm actually I mean, my samples, I guess I was just, sorry, I was just thinking that the quantum samples would be, you know, the coset states, I guess, you know, the state that I get by querying the
Okay.
the oracle.
Okay.
Okay, I mean, we can talk about
Yeah,
that.
the question is not entirely clear. We can talk offline.
I think it does for you, but, so go ahead. Sorry.
So, two questions that depend on it. So the first is this uniquely a thing about Fourier, like K Fourier sparse, or if I have something that is sort of K sparse, but in some other linear combination of my original samples?
I think you can also think about it as k-sparse in some other.
And so the other question is, would I need to know in advance what is the right way to look at the data? You have a speed up because you know this is
Yes.
Fourier? Okay.
Yes, you're absolutely right. So we know you get the speed up because you know that it's sparse in the Fourier domain. If you know another domain in which you can, on which it's sparse, maybe you can do. Yes, you're totally right.
So actually, a couple of you answered my previous questions. I was completely confused because your original distribution is one thing, but then when you have a fixed Boolean function which you are querying, then so the quantum refers to the distribution on the axis, not the distribution on the on the functions. So I think that's one thing. But so here, this resource, is it kind of like the Chermanian dimension in the classical? So is it an analog of that in the quantum setting?
I will.
mean, this resource that you are talking about, the Fourier span.
No, I wouldn't think of it as the VC dimension.
You wouldn't think of
No, I will come to the VC dimension later, but I think the VC dimension for this concept class is not R. I don't think so.
I mean, the quantum VC dimension, whatever it means.
Well, it's not clear what a quantum VC dimension is. That would be an interesting definition, but I don't think that. Okay.
Okay, so,
Yeah.
so
So I have a question. I mean, these comprehend sensing methods, right?
Yes.
It applies to this case.
Yes, you're absolutely right.
So I would expect a loss of repetition, but you're saying that no?
Okay, so in compressed sensing, what's happening is you're actually getting linear sketches of the function in some. Okay, there are a couple of things. The first thing is, firstly, C is no longer a Boolean function, it's a real valued function. That makes it harder, but the model there is slightly different because you don't really get an x comma C of x, but you can apply the truth table of f to a matrix. You apply a matrix to the truth table of f hat. So yeah, okay, fine. What's happening in compressed sensing, I don't know about it completely, but you have a function which is sparse in the Fourier domain. So you look at the Fourier vector, which has k non-zero elements. The model there is you can apply a matrix to the Fourier vector. So it's slightly different from the query model that I'm assuming here. But there we don't, it's very different because we didn't know how a quantum compressed sensing model would look like, but I think that's an interesting open question actually, which we haven't thought about yet. But again, I would like to emphasize the model is slightly different. That's the, if you have any questions again, feel free to stop me. Right, so the second thing I'm going to look at is the DNF, learning DNFs. So what's a DNF? So, I mean, Vedran spoke about AND of ORs. Those are just satisfiability problems, but you could look at OR of ANDs. So a quick example is you have OR of AND. This AND contains 3 variables, this AND contains 4 variables. And a DNF on n variables is S term if the number of terms is at most S. So this is 2 terms, 2, 1, 2. So this has 2, 3. It has a number of variables, n, I don't know, but it has 2 clauses. That's what I want to get at. And the goal is I want to learn DNFs. That is, this is the concept class. C is a DNF on n variables. It has S terms. I want to learn it under the uniform distribution. Again, this is an extremely hard problem. In fact, if you can solve this classically, you can earn about $1,500. I don't know, approximately $3,000. People have put bounties on this problem. It's extremely important for these people, for the classical learning theory people to solve this. Pardon?
3,000.
I know of at least 3 people who have put a bounty of 1,700, approximately 3,000. They care about it a lot. I just want to emphasize that. This is very important for them, classical learning theory people. And And the best known upper bound we have is from actually long, long back. It's an n to the order log n upper bound, and this was proven by Berg-Buet in 90. But quantumly, Schutte and Jackson came up with a beautiful polynomial time quantum algorithm. So this is an impressive thing. I mean, in fact, people are kind of conjecturing that you could maybe show hardness of DNFs, but we know quantumly you can do it in polynomial time. So that's very impressive. And let me quickly tell you how this polynomial time quantum algorithm works. And so the sketch is the following. The first thing is a structural property of DNFs. If you have an S-term DNF, there is a large Fourier coefficient. This is not too hard to show, but this is a nice observation. Now, once you know that there is a large Fourier coefficient, you're using the uniform distribution. The second thing you do, Fourier sampling. That's about it. So you can keep sampling from the Fourier distribution. Remember, if you're getting uniform quantum examples, you can sample from the Fourier distribution. And what Schutte and Jackson do is they keep sampling a polynomial S many times, and they will see one such U. They will see an U which has large Fourier coefficient. Yes?
Just to ask, I mean, this is now about time complexity, not
Yes.
just Fourier complexity.
You're absolutely
not
right.
just sample complexity.
Yes. I'm sorry, I should have mentioned that. Here I'm talking about time complexity, not just sample complexity. Right? So you see one such U, and they construct a weak learner. What do I mean by a weak learner? They construct a function U. This is just a parity of U. And the parity of U agrees with the target hypothesis, target concept on a half plus 1 over S fraction. This is nice, but we are not good enough because you would like to say the target, you would like to output a hypothesis that agrees with what you're trying to learn on most inputs. Let's just say 2/3 of the inputs, not on a half plus epsilon number of inputs. That's not good enough. Well, so what they do is they use a technique called boosting. So boosting is something which, again, was introduced for classical machine learning, and the people who invented boosting also got the Gödel Prize. So it's one of the most important things it's an extremely important thing for classical machine learning people. So what Schutte and Jackson do is they run the weak learner polynomial S many times, and they obtain a strong learner who does very well on most fraction of the inputs. Again, what I would like to emphasize or you to take away, 1 and 4. This is the workhorse of this algorithm, and those are all classical machine learning things. The crucial thing that Schutte and Jackson understand is you could actually sample from the Fourier distribution. And really, if you just understand that and piggyback on the classical machine learning people to do their work, you can have a quantum learning result. How much time do I have left? 10. Okay, finally, I'm going to be talking about my second technique. It's the pretty good measurement.
Yeah.
Yes.
When you say you are talking about time complexity, are you including the time to encode this in a quantum way?
Let's do it offline. No, okay, fine. So so I'm assuming that someone is preparing this for me and just giving it to me as a resource. But that's an extremely important problem for quantum machine learning. I kind of sweep under the rug, but yeah.
Why is it difficult?
Well,
Because it's from uniform, right? Uniform is a bunch of Hadamars, you run it through a linear extension of the DNF thing, and you're done. No?
for this problem, maybe sure. If you have an oracle, you still need oracle.
The implementation of the DNF, right?
Oh yeah, sure, exactly, sure.
That's easy.
Yeah, you're absolutely right. For this problem, it's not a problem. Okay, let me quickly try to talk about the rest of my talk. And okay, so pretty good measurement. We all know what's a concept class. We all know what's a distribution. I've been talking about this all day long. So what's a quantum example? Since the start, it was just a coherent superposition where the amplitudes are given by this distribution. So I mean, if you look at a quantum learner, what's really happening is he's just given t copies of this, and he needs to identify c. And the optimal measurement that he could use could be extremely complicated, but there is something called a pretty good measurement. So this is like a state identification problem. You're given a quantum state, t copies of them. And you know that this quantum state is coming from a family of script C. You want to identify C. It's called state identification. The optimal measurement could be complicated, but there is something called the pretty good measurement, which is pretty good in the following sense. So if P opt is the success probability of the optimal measurement, PPGM is the success probability of the pretty good measurement, then this is clearly true because the optimal success probability is of course lower bounded by the success probability of the pretty good measurement. But what we know is it's actually lower bounded. It's not too bad. This lower bound is not too bad in the sense like this is lower bounded by the square of the optimal success probability. And let me quickly go through the last two parts of my talk where I show where I use this approach. And this problem is a coupon collector problem. If you have lost me so far, I think this is a beautiful puzzle, and I really like this application. Let's just say I have n coupons labeled 1 to n. And what I'm going to do is the following. I'm going to pick a coupon, I'm going to give it to you. You're going to see the coupon number, and you're going to give it back to me. And I'm going to repeat this thing many times. So I'm going to keep drawing coupons. And the question is, how many times do you have to repeat the sampling process before you have seen all coupons between 1 and n? And the answer is n log n. It's a simple probability calculation. So I'm going to look at a slight twist to this, and let's just say we're looking at a variation of the coupon collector problem. There are again n coupons, but I'm going to pick out one coupon, I'm going to keep it on the table. And so the n minus coupons that I have right now, and we're going to repeat the same process. I'm going to pick out one coupon from the n minus 1 coupons, I'm going to give it to you, and we keep repeating this. So I star was the coupon I kept on the table, and I keep finding coupons from n minus 1 elements. And at some point, you should find out what is the coupon that I kept on the table. So I have n minus 1 coupons with me, with one coupon on the table, and the question is, you find what's the missing coupon. So you have to learn the missing coupon. And the similar analysis as before gives an n log n upper bound, and it's tight also. And the question that we actually initially, we were looking at some problem altogether different, which is related to learning, but we hit on that, is the following. What if you're getting quantum coupons? So what do I mean by that? Let's just say I have a superposition of n minus 1 coupons. So I picked out an I star, I kept it on the table. I have n minus 1 coupons with me. So I have a coherent superposition of n minus 1 coupons. And I'm going to be giving you t such quantum examples, the uniform quantum examples on n minus 1 coupons. What is the number of quantum states you need to see before you learn the coupon I kept on the table? And the surprising answer is you can actually do it in order n quantum examples. I mean, it's just a log n improvement, and some of you might not be impressed by this, but it's interesting. I mean, coupon collector is an extremely basic problem, and I think the fact that quantum examples help is very, I don't know, I didn't expect this before, so it's very interesting, I think. And I'm not going to tell you about the analysis, but the crux of the whole upper bound here was to use a pretty good measurement. What we showed is if you're given n copies of the quantum coupon, then the success probability of the pretty good measurement is at least 2/3, so you're doing pretty well. Right, so let me talk about the final thing that I wanted to tell you about. That's the weakness of quantum examples. So far it seems like quantum sort of helps, and it's pretty cool. Standard pack learning. So recap back, second or third slide, the original pack learning framework. For every distribution and for every concept in the concept class, you want a classical learner with high probability to output a hypothesis that's approximately close to the thing that he's trying to learn. And the question that I care about here is the number of labeled examples he sees. So classically, what do we know about this? So for every concept class, there is something called the VC dimension, or the Vapnik-Chervonenkis dimension. It's just let's just say you give me script C and the truth table of all the concepts in my concept class. I can just tell you something called, this is the VC dimension. You don't need to know anything about learning or something. It's just a purely combinatorial parameter. But what's surprising is classical pack learning is actually characterized by the VC dimension. So just knowing this combinatorial parameter tells you something already about learning, which is kind of interesting. And I'll just make this quickly formal. In fact, it's called the fundamental theorem of pack learning. Suppose you have a concept class whose VC dimension is D. Then Bloomer et al. Showed that you need D over epsilon classical examples to learn the concept class. And they proved an upper bound that was slightly worse than this. And it was a long time open problem. What is the right answer? Because pack is so important for classical machine learning people. And a couple of years back, Steve Haneke showed that actually there is an upper bound of D over epsilon as well. So D, that is a VC dimension, actually characterizes classical sample complexity. So what can we say quantumly in terms of the VC dimension? So actually what kind of inspired this work? Maybe it was the fact that this classical people did the hard work for us. So we have a classical upper bound already of D over epsilon by Steve Haneke in 2016. Atici and Cervelli actually looked at this problem in 2004, and they proved the square root of D over epsilon lower bound. And what we showed after a year after Steve Haneke's result was actually you could prove even a lower bound of D over epsilon. So remember the classical upper bound carries over to quantum because a quantum learner could always just choose to measure his examples, and he could just run a classical learning algorithm, but we also show a lower bound of d over epsilon. And again, I'll just give you a 2-line proof idea. The idea is to reduce it to state identification problem. And we show that if the success probability of the optimal measurement is at least 2/3, the success probability of the pretty good measurement is at least 4/9. And if this was satisfied, then t is at least d over epsilon. And yeah, this shows that quantum examples are no more powerful than classical examples for packed learning. So packed learning is something people actually care about in computational learning theory classically. And we looked at a quantum version of this where you're given quantum data, access to a quantum computer. We show that quantum examples are no more powerful than just classical examples. And like something we have been kind of speaking about throughout this day is, kind of machine learning is sort of noisy in a way. So if you get real, there's some sort of, there are formal learning models called agnostic learning or learning under classification noise. These are theoretical ways where you can model noise in data. And what we show is even in this agnostic model and this classification noise model, quantum examples do not provide an advantage to sample complexity. So if you look at packed learning, agnostic learning, learning under classification noise, quantum examples are really not providing you an advantage. So yeah, that's about it. And you have just a couple of slides and it should be done. So first thing is, since I'm talking on day one, and I think a subset of you might have heard of this talk by maybe Ronald, my advisor, my former advisor, or me, I'll just give a few directions which I'm thinking about right now, and I'd be happy to talk about this later. The first thing is, can we get more mileage out of Fourier sampling? It seems like it's an extremely powerful tool. Can we really find more examples where it helps? And one thing that I'm very interested in, so Schutte and Jackson, they showed you can learn DNFs, which are depth 2 circuits. Can we extend the result to depth 3 circuits? And already their techniques break down immediately. So we need something slightly different. And even more ambitiously, can we pack learn DNFs? So, Schutte and Jackson showed you can learn DNFs under the uniform distribution, but can we learn DNFs under all distributions? And this is believed to be hard classically. What I mean by believed, there are some, you can rely on some hardness problems on which you can show that if the hard problem was solvable, then you can pack learn DNFs, but we believe the hard problem is not solvable. So if we had a polynomial time packed learner, that would be very interesting. Next, so Scott Aronson actually asked this question, and he calls it one of the 10 semi-grand challenges of quantum computing. Can we learn not just depth 2, 3, 4, can we learn constant depth quantum circuits in quantum polynomial time? I think this is an extremely important problem. And not just AC0, because you can't convince practical people why AC0 they should care about, but I'm going to say TC0 is something you should care about. So what is TC0? So TC0 is and, or, not, and threshold gates. So threshold gates are something that you might have seen that comes in neural networks. So these are gates that are given weights, and if the inputs satisfy some weight criterion, then it outputs 1, otherwise it outputs 0. So sort of if you can show TC0 is learnable in quantum polynomial time, this is a theoretical way where you can show that quantum helps in learning the weights of neural networks. And that is, I think, an extremely important problem to understand. And slightly abstracting away, can we learn quantum circuits? This is vague, and so what I mean is, let's just say you have a family of quantum circuits, and you keep obtaining, on the all 0 input, you get a quantum state out, and you keep obtaining the output quantum state. Can we learn the quantum circuit up to some isometry or just output a representation of the circuit in some sense? And some more open questions is, can we improve our k to the 1.5 upper bound of sparse Boolean functions to k log k? That's, I think, very interesting. And so, if you look at packed learning, you wanted the learner to do well under every distribution. That is something very ambitious. If you look at practice, people don't care about all distributions. They just care about some useful distributions. And in fact, we know under the uniform distribution, we get a huge advantage. And the lower bound and the distribution we use to prove the lower bound is under a distribution which is almost peaked at one point and uniform elsewhere. So it seems like there's a big trade-off. When it's almost peaked and uniform elsewhere, you get no advantage. but when it's uniform everywhere, you get an advantage. Is there some sort of transition in terms of min entropy of the distribution or so on? So because PAC is so important, I think understanding these kind of trade-offs is also very interesting. And finally, I would like to say that in my knowledge, most of the speedups that we are having right now is under the uniform distribution, which is sort of embarrassing. We should find more distributions where actually quantum provides a speedup. I mean, in this direction, there was some work recently, but I don't think we still have a convincing example where quantum provides a speedup under non-uniform distributions. Fine, let me conclude. So this was my classical Pac-Man. This is the quantum Pac-Man. He's supposed to be sad here. So I mean, the sample complexity of quantum Pac is the same as complexity of classical Pac. But I mean, when we started, we know that under the uniform distribution, quantum examples seem to provide a tremendous amount of advantage. I mean, we saw lots of examples. Notoriously hard classical problems are easily in quantum polynomial time. But again, what I would like to emphasize again is, I mean, this field is pretty young. There's not much that we know, and there are not many examples where quantum significantly improves ML. What's nice about it being young is you can just read a few survey papers and you're kind of the master of the subject and you can already start improving the field. Yeah, I think I would like to conclude with that. I think there are a couple of books which are interesting and there are a few surveys. If you read that, you're the master, you can already start contributing. With that, I thank you for your attention.
Thanks a lot, Srini. Any questions?
So about the last bullet on your previous slide about non-uniform distributions.
Right.
Um,
Yeah, okay.
I guess I'm a little surprised by what you said because I would imagine that these Fourier sampling, that these sort of Fourier-based quantum algorithms are actually pretty stable to sort of disturbance of the state, like, and that maybe you could even take, you know, a sizable fraction of the state and just, you know, blank it out and that the sort of Fourier analytic information would still come through with some error. Is that not what happens?
Okay, sure. Good point. So, I mean, if supposing, yes, I'm going to. So if supposing you have some errors in the quantum state, let's just look at the simple case. You have a quantum example, and let's just say every label that is C of x gets flipped with the same bias, C of x plus beta.
Okay.
Then if you do the Fourier sampling, nothing is changing. Sure, so it's sort of robust under that noise model. But what I meant there was some noise model which people actually care about in classical machine learning and where you can actually do something quantumly efficiently also. There we don't really have any provable quantum speedup, I would say, yet. Does that answer your question?
But what about the case where you just pick a random, let's say, you know, 1/10 of the domain, and you just give me like the reject symbol there or something like this? So, I mean, to me that sounds like a sort of reasonably motivated model. I mean, I just mean uniform distribution on all but
A subset.
You know, a constant fraction.
So if you have the uniform distribution on just a subset of all,
On like 9/10 of the input, I have uniform distribution. Everywhere else, I get nothing. It seems like these algorithms should still work in that case.
I would think they would work as well, but I wouldn't give my word for it. But I would think they would, because I mean the inner product is so small, you could assume that the origin, right? I would think that. I think our algorithms are robust enough. But what I meant to say is, let's just say you have some sort of a funny distribution, like a product distribution or an exchangeable distribution. Can we have quantum learning algorithm?
Any further questions?
So, I mean, there are many ways you can tweak this model, right? You can change a bunch of things, but there's one very quantum thing you can ask, and I don't know if it's obvious. Suppose my measure isn't to output a classical specification of a function, which I will use forever, but I'm just asked to label one example. So in this case, I don't have to measure my quantum examples, right? I can keep them in quantum memory,
Okay.
and then do a joint measurement on this one example in the entire thing. Does anything different happen?
If you could repeat the question.
So this is like this inductive versus transductive learning question.
So you're saying, maybe I didn't get your question completely. So you're saying you're given T quantum examples, but
And I will be asked to label only one.
that's a class. So you're okay. Yeah. So you're given T quantum examples, and you're just in the end you're asked to label one.
Yes. Does anything change in any of them?
I don't think it changes. I mean, to me, it doesn't seem obvious that anything will change. In fact.
But in classical theory, it does. Well, if you know which one you'll be asked about.
Well, I mean, I'm not assuming anything about the question that you're going to be asked about at the end. I'm just saying, I mean, in fact, another way to rephrase what the learning model is, you're just given t examples, you're given t plus 1th example, but not a label. You're just given an x. Can you label that x, comma c of x with high probability? That's another way of phrasing this learning model.
Is this equivalent to say
Yes.
you output a hypothesis function in the quantum case?
I want to say they're equivalent, actually. Yes, I think I can, yeah, we should talk about it offline, but I think they're equivalent.
Further questions?
Sure.
I mean, you started now at MIT with Aram,
Right.
So Aram and Hallgren, they have a paper from a while back where they generalize quantum Fourier sampling to some dispersing unitaries, and it still works, everything works out fine. So I'm sort of asking the complementary question when you say, okay, let's get more mileage out of Fourier sampling. Let's not do Fourier sampling, but something else which is dispersing. Can you somehow reverse engineer different classes? What do you think?
I'm not sure about the result of Aram and Sean, but was it related to Shor sampling and so on? Or I'm not sure. Maybe I don't have an answer to your question even.
Anybody else? No? If not, let's thank the speaker one last time. All right, well, that concludes it for the session. Shadi?
Yeah, so just a quick announcement that we're going to close this room after the date, so we'll have discussions having the QuiCS. You know, remember to get your loan before the
On the second part, when you were thinking, so basically there is some advantage, and so all these remarkable advantages was about the running time, right? Not about query complexity.
Not all of them. So DNFs is about the running time.
But they're, because of the distribution, was restricted, right?
No, but I mean, even if you just use a pretty good measurement for some reason, it's not clear that